Thank you for giving me the opportunity to give this talk. So this is based on joint work with Zhonghi Chen, Yongmin Cho, Alain Pasleg, and Elias Suvento. And I give the ePrint reference if you want more details after the talk. So it's about some security notions of fully homomorphic encryption. Okay, so just a few words about fully homomorphic encryption. So it's an FHE scheme is a bunch of algorithms, keygen, enc, eval, and dec, which works as a public key encryption algorithm, except for the eval function. So eval allows you to evaluate a function on ciphertext on the plaintext underlying some given ciphertext, without decrypting the ciphertext. So, so here I give the correctness equation, but I think it's more, it's clearer with a picture. So you have a client which has some messages, MIs, and the client wants to delegate some computation to a server. And the way the client delegates the computation is by sending encryptions of the MIs. So these are the CTIs, a circuit or a function F, and some evaluation key. And then the server can compute on the ciphertext based on the evaluation key and the circuit, and sends back a ciphertext that hopefully decrypts to F evaluated on the MIs. Okay, so so today there are a bunch of FHE schemes that exist. So here I'm listing the most competitive ones in practice currently. So out of the three families, the oldest family is BFV, BGV, which is a bit more than 10 years old. And the native plain text space for those schemes is vectors of elements in a finite field, where k is some parameter and n is a very large integer. So typically n would be around 2 to the 15 or 2 to the 16. And then the native operations that we have on this plain text space is addition component-wise, multiplication component-wise. We are also allowed some kind of FP to the K automorphisms component-wise, and rotations of the coordinates. So we have a vector, and we take the coordinates, we shift by one, and the coordinate at the end we put in front. So these are the basic operations that we are allowed. And once we have these operations, we can do quite a lot. Yeah, if I move to the second family, so DM, CGGI, also known as FHE and TFHE, the native plain text space is bits. So you have like extensions with small integers, I don't know, like 4-bit integers. The basic operations that you have is binary gates on those bits, and then the ciphertexts are in LWE format, except that you use ring LWE internally. And the last family out of the three, the most recent, is CKKS, where the plain text space, the native plain text space, is vectors of complex numbers or approximations to complex numbers. Again, you can add and multiply component-wise. You can conjugate component-wise homomorphically, and you can take the coordinates of a vector and rotate the coordinates. So again, the ciphertext format is ring LWE like BFV and BGV. So now let me classify these two families. So one can say that the first two families are kind of exact FHEs in the sense. So either bits or vectors of finite field elements. And oppositely, CKKS is approximate in the sense that the underlying data is approximations to complex numbers or real numbers. So here is the operations are not exact in this sense. If you add, you are adding approximations, so and then you add some more noise on top of the approximations. So it's more akin to floating point arithmetic if you think of plain text computations. Okay, so I want to mention that there is an exact mode as well for CKKS, and I'm not going to talk about it on Thursday, so it's I recycled the slides and now everyone sees it. Okay, so INDCPA security is a basic security notion that we may be interested in for FHE. It's the same as for public key encryption. So informally, what cannot distinguish between encryptions of two different plain texts of the adversary's choice. Okay, so there was a stronger notion of security put forward recently by Lee and Michencio, which is called INDCPA-D security, where the goal is the same. You cannot distinguish between encryptions of two different plain texts, but you are allowed, as an adversary, you're allowed a bit more. You can ask for decryption of ciphertext for which it is supposed that you know already the underlying plain text. So for example, you can ask for an encryption of 1 and then ask for the decryption of that ciphertext. Or you can ask for an encryption of 1 and another encryption of 1. So you have two ciphertexts that both decrypt to 1. You ask to homomorphically add those ciphertexts, and then you can ask for decryption of the result. In principle, it's not supposed to give you much information because if you know that the first two are decrypting to 1, the addition of the ciphertext should decrypt to 2. So you don't learn much by allowing this decryption of this type of ciphertext. So more formally, so you can ask for encryptions of plain text. I mean, we formalize it this way so that the challenger knows the plain text underlying all ciphertexts. You can ask for encryption of challenge plain text. So you send M0 and M1, and one of the two is going to be encrypted. You can ask for evaluations of well-formed ciphertexts, of ciphertexts that are already in the database. And you can ask for decryptions of ciphertexts that are already in the databases and for which the decryption doesn't depend on the underlying bit B. So otherwise, it would be trivial. And then the adversary has to guess B. So that's the type of security that we are going to consider during this talk. Yes?
Sorry, simple question. Is there any limit on the F that the adversary can choose here?
Any F which is allowed by the homomorphic encryption scheme. So
Okay.
for those, I considered any F.
Okay, thank you.
It's like a follow-up question to that. I was kind of interested too. So typically, like, I guess you have to perform bootstrapping if F is, let's say, the depth is too high. So is it the job of the challenger to know, when given this description of this function F, the depth of the circuit?
Sorry.
Also, like, can F, so typically, like, I guess, like, when you do these evaluations on some circuit, you have to do this perform like bootstrapping steps, but for that, wouldn't you need to know how deep this function F is? And are we implicitly assuming that this function F, like the depth and everything, can be computed efficiently by the challenger?
Yeah, so you may have to bootstrap. I'm assuming implicitly that the description, I mean, here the definitions are not very formal, but I'm assuming implicitly that the description of F leads to a given circuit.
Okay, thank you.
We could go even further and ask, I mean, allow the adversary to say when to bootstrap and so on. So it's related to a specific way to homomorphically implement the circuits.
Okay.
So during the rest of the talk, I'm going to give attacks, and we will not need this kind of things, but it could matter for getting rigor, to getting proofs and to getting proper, I mean, secure software. Any other question on the notion of security? Okay, so in this paper, there were two claims. So one, there are many claims in the paper, but two that I'm going to focus on during this talk. So one is that an approximate homomorphic encryption scheme can satisfy INDCPA security and still be completely insecure. So that was a statement made in the paper, and I mean, then it's in opposition to what happens for exact schemes. when applied to standard exact encryption schemes, INDCPA-D security is perfectly equivalent to INDCPA security. So in particular, CKKS is being singled out as insecure in this work. So these statements, they raise a bunch of questions which are not answered very clearly in the paper, at least in my opinion. So completely insecure is not, I mean, it doesn't say what it means precisely, unless we consider that breaking INDCPA-D security brings total insecurity. Exact is also underdefined in the paper. So does it mean exact data, or does it mean correct, or is correctness heuristically correct, or provably correct? And which error probability? So there are a bunch of questions or imprecisions that these statements raise. So here in this talk, what I'm going to give is more attacks, more INDCPA-D attacks, and in particular, INDCPA-D attacks on schemes that work on exact data, including BGV, BFV, DMCGGI, and CKKS, including the exact version of CKKS. So as a whole, when it comes to INDCPA-D security, I think the takeaway message is that I mean, it matters for all schemes, and CKKS shouldn't be singled out.
Damien, can I ask a question? So you might come back to this later on, but what should we feel about these kind of attacks? Is it a practical attack, or so is this a good thing or a bad thing?
I mean, when you have attacks, usually it's bad. Huh?
But it feels like a very a conceptual attack to this. So is this something that we can exploit, or?
Yeah, so I'm going to motivate a bit.
Okay, great, thank you.
Slides, yeah, because I mean, this notion of security is not totally. I mean, it's a bit hard to grasp. I think so. Yeah, let me give a few examples of relevance. So why is INDCPA-D security relevant? So one of the use cases of FHE is that you want to externalize a computation while preserving confidentiality. So in particular, you are encrypting the data on which you are computing. So if you do this and the client receives the result, then why would the client make the output of the confidential computation public? I mean, if your inputs were very confidential and you wanted the computation to happen in a confidential way, and you are okay to pay for the cost of FHE to do it, why would you make the output public? So that's, I think that's it's a non-trivial question. And if you don't make the output public, INDCPA-D security is irrelevant, because the whole point is that you can see the decryptions of some ciphertext, at least for honestly computed ciphertext. So here is one motivation. So you can think of a scenario where you have some kind of weak variant of security with ciphertext validity oracle. So imagine that I'm delegating a computation to Amazon with FHE. Then Amazon sends me the result back. And when I decrypt, I get something which is weird, which I didn't expect, which is either it gives some completely random value or something which is the opposite of what I was expecting. Maybe I will complain. Maybe I will suspect that Amazon didn't do the work properly and is just sending me a random ciphertext. So I can complain, and then I'll say, yeah, your computation is weird. Please redo it. Okay? And just this bit of information is more than CPA security. If you tell the adversary that something odd happened, you are already giving more information than what is captured by INDCPA security. So that's one scenario where INDCPA-D security is relevant. Another scenario is when you start using FHE for some kinds of multi-party computations. So like the simplest example of this is threshold FHE, where different users compute on data, on different data that they have. and then they jointly decrypt the result of the computation. So in this case, the adversary is typically one of the users. And then just by design of the scheme, the adversary gets the result of the computation because it is one of the users. So in this, if you want to go towards this kind of schemes like threshold FHE or extensions, then you can assume that the adversaries, even if the adversary is following protocol, the adversary sees the results of the computations. So for threshold FHE, you may need much more than INDCPA-D security, but that's really a minimal requirement. I mean, if you don't have INDCPA-D security, it's going to be very complex to get sufficient security for threshold applications. So that's two examples to motivate a bit INDCPA-D security. Okay, so now let me move on to attacks on CKKS. So the plain text space is vectors of complex numbers up to some precision, and I can add and multiply in parallel. So here I will not even add or multiply, actually. I will do nothing homomorphically. When I decrypt, I get an integer mod Q, and in the most significant bits you have zeros, and in the least significant bits you have some scaled version of the plain text M. So delta is a public scaling factor, and M is some real number between 0 and 1. Okay, so we get 0 and delta M when we decrypt. So how do we decrypt? So a ciphertext is of the ring LWE form, AB which are both ring elements. I don't need much algebra here. I just need to know that decryption is basically a linear operation. So I'm using the secret key S. I'm computing AS plus B, and that's essentially delta M. So decryption is just linear. Okay, so how do I attack it for INDCPA-D security? So decryption is a linear function of S, okay, up to the scaling factor, but the scaling factor is public, so I can forget about the scaling factor. So I can ask for an encryption of 0 and ask to decrypt it. Okay, so I know AB, and then I learn A times S plus B. So I have an equation, a linear equation in S, and this reveals S. Okay, so just one decryption reveals the secret, and that's it. And it's a key recovery attack. Okay, so there is a countermeasure which was proposed by a subsequent work of Lee, Michiencho, Schultz, and Sorel, which consists in adding noise when we decrypt. And the way this is implemented is by bounding the contributions of all errors due to encryption and evaluation. So we have like an absolute maximum error bound of all the errors. And then to this bound, we add some noise. So basically it's noise flooding. So we add a gigantic like Gaussian noise on top of it. And then we can actually prove that when we do this, the scheme becomes secure against INDCPA-D attacks. And the proof of security is basically that the output, you can simulate the output from the knowledge of the expected output plaintext. So that's sufficient to simulate the output, and that gives a security proof. And in the same work, they showed that such a large noise is actually necessary. So if you decrease the noise, you have a distinguishing attack. Okay, so let me move on to the case of exact schemes. Okay, so assume the scheme is exact. So the intuition is that the decryption queries do not help the adversary, because for any valid decryption query, that is the corresponding plaintext does not depend on the challenge B. The adversary already knows the underlying plaintext. I mean, it's almost a tautology given the definition. The adversary is allowed to decrypt only if it knows the underlying plaintext. So again, if this holds, then you can simulate decryption queries yourself. You don't need an oracle. But there is a caveat. the intuition to work requires that we have perfect correctness. So if I let, or near perfect correctness, so if I let PR be the maximum over all possible circuits and all possible inputs of the probability that the eval of F in the encryptions doesn't decrypt properly, okay? So if I look at this probability, the equivalency between CPA and CPA-D security holds if this probability of incorrect decryption is extremely small, like unnoticeable for the adversary. Okay, so if this doesn't hold, if we don't have a very strong notion of correctness, then there is a semi-generic attack. So let's assume. So it's not an attack that always works, but let's say it's an angle of attack that would work for all existing schemes. So let's assume that so we have this error of this failure probability, and let's assume it's not that small. So I'm assuming further that the adversary knows a circuit F and two tuples of inputs, the MIs and the M', such that F on the MIs homomorphically reaches the maximum error, the maximum decryption error failure probability. F on the M' has a much lower decryption error, but the two functions, the function evaluates in the same way on the two sets of inputs. So I have a given function which evaluates in the same way for the MIs and the M', but such that if I homomorphically evaluate on the MIs, I have a big error, a big failure probability. And if I evaluate on the M', I don't have a big failure probability. Then the adversary could just request encryptions on the MIs or the M', depending on the challenge bit, request the evaluation of F, and request decryption. If there is a failure if there is a correctness failure, then it's more likely that the MIs were encrypted than the M'. So if you have some difference of failure probability for inputs that evaluate in the same way for the same function, then you can exploit this difference. Yes, there is a question here.
Thanks. Yeah, my question was, what if you don't have perfect correctness, but if the probability only dependent on the function F? Could you still have an attack, or would this work?
I don't know in this case. So yeah, so this example actually works for most of the schemes I'm aware of. Yeah, otherwise I don't know. Yeah.
Okay, thank you.
Oh, Martin has an attack already.
But isn't that like similar for the CCA attacks? Like you get, it's in this way you learn something about the
yeah. So it's yeah, indeed. So I mean, it's very closely related to the CCA attacks. So on lattice-based schemes.
Yeah.
So indeed. So I mean, the attacks that we are going to have are closely related to these like CCA attacks or side channel attacks, as we discussed this morning. Except that we are not, I mean, we are allowed a much smaller set of queries. So we are allowed, I mean, in CCA attacks, you're allowed to decrypt any kind of ciphertext. Here, you're only allowed for decryption of ciphertext for which you know honestly generated ciphertext.
See about the error, right? So you
Yep.
know the error, then I move it out of the accepted range of it.
Yeah, but how do you? Yeah, I mean, you need to move the error out of the range, but you are not allowed any kind of operation to do it. You're only allowed valid homomorphic operations. So it's somewhat active, but not much. So you're not allowed much. Okay, so what about correctness in practice? So if you look at FHE libraries, they are not correct. And I mean, they are very far from perfectly correct. So the failure probability for the libraries that we looked at goes from 2 to the minus 15 to 2 to the minus 50. And on top of this, it's derived from heuristic error analysis. So why do FHE libraries proceed in this way? Because I mean, it leads to much more efficient schemes. And for the primary use case of FHE, INDCPA security suffices. So people, implementers have been mostly focusing on INDCPA security, and in that case, I mean, decryption failures only impacts functionality, but not security. So during the rest of the talk, I'm going to explain how to exploit decryption errors to mount INDCPA-D attacks on the exact schemes. So that's a game that we are going to play.
Is this failure probability the variance? Is it depending on the scheme we use or the number of times we evaluate the ciphertext?
So that's a good point. So this failure, so the 2 to the minus 15, that's quite large, I find. I've seen it only once for some variant of TFHE. 2 to the minus 50 is quite small compared to most libraries. I would say usually it's around 2 to the minus 40, 2 to the minus 35, this kind of values. Sorry, what was the rest of your question?
So does the failure probability change depending on how many times you operate on this site?
Oh, yeah. So this one I like, because indeed, I mean, there is no randomness, but every time you evaluate, you increase the decryption error probability. So yeah, so the more you compute, the higher the decryption probability.
Okay,
even though you don't inject any kind of randomness. So mathematically, there is something dodgy going on. So if you evaluate a circuit with 2 to the 40 gates, you will get close to probability 1 of failure for some schemes. Okay, so we'll start with an attack with for BFV, BGV as a warm-up. So quick reminder on BFV, BGV. So the plain text space is polynomials mod P, and we can add in parallel. We can do more things, but I'm going to add only. And the ciphertext, it's a pair of polynomials such that A times S plus B has M in its most significant bits and E, some error E in the least significant bits. So when I decrypt, I get an integer mod Q, such that M is in the most significant bits, the plain text is in the most significant bits, and the error term is in the least significant bits. So to decrypt, I'm computing AS plus B mod Q, and to recover the most significant bits, I'm just rounding to only get the most significant bits. Okay, so let's see how to attack this one. So we are going to assume that the noise is computed, the upper bound on the noise is computed in some way. So in theory, to get correctness, you need to bound the contributions of all errors for all possible inputs. In practice, sometimes, not all libraries, so I will discuss it a bit later, we may use heuristic bounds, and we may assume that the noise underneath CT1 and CT1 plus CT2. So let's say I have some noise in CT1 and some noise in CT2. In the worst case, this noise can be added. On average, we would expect that it's not really added because we take two Gaussians, two independent Gaussians, we sum them, and then the standard deviation doesn't grow as much as the triangular inequality. Okay, so if the two noises are the same, have the same standard deviation, the triangular inequality would increase the noise bound by a factor 2, and a heuristic noise bound would increase the noise by only a factor square root 2. Okay, so here is the circuit that we consider. So we start from an encryption of 0, and then for k times, we add the ciphertext to itself. Okay, so we take encryption of 0 and we add it with itself. And then we take the new one, we add it with itself, and so on and so forth. We do it k times. So the estimated noise goes as 2 to the k over 2. So we pay square root 2 every time. But the real noise goes like 2 to the k because, I mean, it's not independent Gaussians. It's just the same noise all over the place. So when we add a quantity to itself, it grows by a factor 2, not square root 2. So the fact that it grows, I mean, it grows by 2 to the k instead of 2 to the k over 2. So the 2 to the k over 2 says that the computation is deemed legitimate. So it shouldn't grow so much that it fails. But in practice, it actually grows more than this. And if you choose k correctly, basically you are putting the noise term into the most significant bits. And when you ask for the decryption, you get the noise terms. Okay, so you get the input noise terms. And if you have the noise terms, then you have a linear equation in the secret, and you can recover the secret. So this gives a key recovery attack just based on k homomorphic additions. So I want to say that this is an adaptation of a work due to Go, Nabokov, Suvento, and Johansson, which is going to be published this year at USENIX. And there was an independent, and the result was concurrently obtained by Shekri, Sirdeh, Budgiga, and Bulten, and whose work is going to be presented at Crypto. Okay, so one question is whether it works on OpenFHE. So OpenFHE, I'm looking at OpenFHE because it claims to get INDCPA-D security for CKKS. I think it's the only library that has such a claim. And it has measures in place for correctness of exact schemes. So it also claims that exact schemes can be made correct. Okay, so we tested on OpenFHE's BFV implementation with some parameters. We started with an encryption of 0 and we repeated 44 times. And for the parameters that we have, the estimated error probability is gigantically small. But decryption gives the initial noise and we recover the secret. And as you can imagine, there are only additions, so the attack is instantaneous. But why does it work? Because OpenFHE doesn't use heuristic bonds for homomorphic addition. It uses a triangular inequality. So, I mean, the bond that they have on noise should be exact. I mean, it should be correct and should always work. But still, the attack does succeed. So there is something dodgy going on. So it turns out that so we were a bit surprised. So we went into the library, we looked at the code, and there is an error in the handling of addition error bonds. So for k addition, OpenFHE multiplies the error bond by a factor k. But if you look at the circuit that we have, it's k additions, but the error grows as 2 to the k. So there is a software issue here, and what we broke by testing the attack on OpenFHE is actually the implementation, not what it was supposed to do.
Can I ask a question? So it seems so weird that just adding stuff, you get an error of 2 to the k. So can you detail a bit what happened there?
So first time you add a number with itself, you double. Then you take the result, you add it with itself, multiply by another factor 2. You take the result, you add it with itself, another factor 2, and so on and so forth.
Okay.
So if you want to enforce something like with k addition, it goes only by a factor k, you have to put some constraint on, you have to have a way to avoid such circuits. Maybe you need to enforce some freshness of some ciphertext that you're adding. But still, this is not trivial because something that you want to do is like chains of additions. If you compute inner products, you want to add like all this stuff, and as a result of the previous one, you are going to use for the next one, and so on. So I'm not saying it's not possible, but you have to be a bit careful on the semantics of what you allow and what you disallow for given error bonds. I think it's doable, but you have to be a bit careful. Okay, so I'm moving to the next schemes. In those cases, I will attack the bootstrapping algorithms. So it's going to be a bit more technical than attacking addition. Okay, so let's start with a few anti-FHE. So the plain text space, it's elements of 0, 1, so just bits, and we are allowed binary gates. A ciphertext is a vector of mod Q elements, such that A inner product S plus B is close to Q over 8 times the message. Okay, so there is a Q over 8, which has a purpose for evaluating binary gates. So M is in the most significant bits, and the error is in the least significant bits. So to decrypt, we are again evaluating A inner product S plus B, mod Q, and then we round to the most significant bits to recover the plain text bit. Okay, so how does DMCGI bootstrapping work? So it's a bunch of different steps which form a loop. And because this is a loop, you have to, we can think of a starting point. So I'm starting from top left. It's a bit arbitrary, but I think that's the choice which is made most often. Okay, so at the top left, I start with LWE ciphertext for key S and modulo Q. Then there is a first step, which is called mod switch, which goes to LWE ciphertext for the same key, but modulo 2n, where n is the ring degree that is being used in bootstrapping. So what is mod switch? I'm just dividing by Q multiplied by 2n and rounding. So it's really rescaling and rounding. Then there is a complicated operation called blind rotate, which outputs a ring LWE ciphertext of degree n with some other key S prime, modulo Q, so the same modulus as at the beginning. This step is much more complicated, but we don't need to see how it works. Then we have a sample extract, which outputs an LWE ciphertext from the ring LWE ciphertext. So this step is algorithmically trivial. We just throw to the trash most of the ring LWE data and keep a single LWE ciphertext. And finally, it finishes with a key switch, which allows you to go back from key S prime to key S. Okay, and I also don't need to explain really how this step works. Okay, so all this comes with noise variances, at least heuristically. In practice, there is no addition of randomness anywhere in the process, but we still model noise heuristically with variances. So the smallest variance, the smallest noise that we have is after blind rotate. So the purpose of blind rotate is to decrease the noise. So that's it's a complicated operation, but what it achieves is decrease the noise so that more computations can be done. Okay, so the smallest noise is after blind rotate. Then we do sample extract. It doesn't increase the noise. Sample extract is a trivial operation. Key switch is the first non-trivial stuff when the noise increases. It adds some more noise. So the noise variance goes from sigma blind rotate square to sigma blind rotate square plus sigma key switch square. Mod switch adds some other error term. And then before blind rotate, we have the largest noise variance, which is the sum of three terms with a noise term due to the output of blind rotate, a noise term which is due to key switch, and one which is due to the mod switch. So just bootstrapping like this is not very interesting because we take a ciphertext and we output another ciphertext with a similar noise for the same underlying plaintext bit. What's interesting in DMCGI is that you can add or evaluate a gate at the same time as you bootstrap. And when you do this, you have to add two ciphertexts at some stage. And usually this is done at the mod switch step. So instead of having one LWE ciphertext, you take two LWE ciphertexts, you add them up, and then you do the blind rotate. So you add, you do mod switch, and you do the blind rotate. So the effect of this is that it increases the noise variance before blind rotate. So it multiplies sigma blind rotate square by a factor 4, as well as sigma key switch square by a factor 4. So that's, we have the largest noise when we do a gate bootstrap and just before blind rotate. Okay, so why do I look at those noise terms? Because the larger the noise, the larger the probability of decryption failure. So if I have a larger noise, it's more likely that now it doesn't decrypt properly. So that's why I focus on this step. And gate bootstrapping fails if the noise spills over to the plain text space. And after mode switch is when the noise is the largest. So if gate bootstrap fails, it gives a strong indication that the mode switch error was too large. So maybe sigma BR or sigma KS are too large, but I mean, overall, the sum of the three is too large, and maybe it was just due to the mode switch additional error. Okay, so what is mode switch? So as I said, we scale, we divide by Q, we multiply by 2n to go from modulus Q to modulus 2n, and we round. So what is the effect of this? So it's adding some rounding noise to the decryption. So if CT inner product SK is E, CT prime inner product SK is E plus a rounding noise inner product secret key. Okay. Interestingly, so if a failure tells us that E rounding inner product SK plus E is larger than some threshold, and interestingly, we know the rounding error. So we have because we round publicly. I mean, it's an operation that is publicly made on ciphertext. So we have an equation of the form E round inner product SK plus E is larger than some threshold for a known E round. Okay, so this is like algebraically, it's very close to what happens for CCA attacks on lattice schemes. Here we are in the setup where when this happens, we have very strong information on SK, and we can just complete the attack with some statistical analysis. So once we have a few errors like this, the secret key is almost always completely determined. And because when this happens, it means that SK is very well aligned with E round. So E round gives a good indication on the shape of the secret key. Okay, so in practice, we considered Zama's TF-HTRS library, and for default parameters, the decryption error probability is around 2 to the minus 40. So we didn't run the attack because we would have had to do 2 to the 40 bootstraps, and the bootstrap in single thread CPU is 10 milliseconds. So if you add this up, it goes to several hundred years, single thread CPU. We could use like accelerated hardware or whatever, but we just simulated that 256 decryption errors suffices, and we also did an attack on toy parameters. I want to observe that there are parameter sets for which correctness is much poorer than this, and also the attacks extends to a threshold FHE based on CKKS, on CGGI. Sorry. Okay, so let's move to CKKS. So we also have an attack on CKKS bootstrapping. Okay, so CKKS bootstrapping has 4 steps. S2C, which is a homomorphic evaluation of a discrete Fourier transform. Mod raise, which doesn't do much except forgetting about some modulus. Or it's mostly syntactic. C2S is the homomorphic evaluation of an inverse discrete Fourier transform, and eval mod is computing a mod 1 function homomorphically. So I'm going to focus on eval mod. So this is the step that we are going to look at. So eval mod is implemented by a polynomial approximation to the mod 1 function. over a given number of periods. So let's call the number of periods 2k plus 1 because it's symmetric around 0. So the higher k, the more costly this gets, because then we need a polynomial approximation of higher degree. So that means that we need to homomorphically evaluate a higher degree polynomial, which takes more time and more depth. And the smaller k gives a higher probability of error, because maybe the input is outside of the range now, outside of the approximation, the polynomial approximation domain. If the eval mode input is not in the approximation range, then the output is totally nonsensical. So if we want to evaluate mode 1 on something which is not in the approximation range, but we still use the approximating polynomial, it's not approximating, and it gives the output of the polynomial, which has nothing to do with the mode 1 function. So it's nonsensical. And when that happens, we also have an equation of the form x inner product sk plus e larger than some bound, where x is known. So it boils down to, at the end, it's the same equation as for DMC-GGI, and we can complete the attack in the same way. So as an example, so I'm taking OpenFHE because it claims INDCPA-D security for CKKS. The probability of decryption error, bootstrapping error for OpenFHE goes from 2 to the minus 22 to 2 to the minus 57. So it's, I mean, it is broken by this type of attacks. So if you bootstrap sufficiently many times, you will see bootstrapping errors due to this eval mode polynomial approximation, and then you can recover the secret key. Okay, so a few concluding remarks. So the main takeaway is that if you are interested in INDCPA-D security, you should not just look at approximate schemes, but also exact schemes. So all of them, actually, I mean, all those that are competitive today, all those schemes can suffer from INDCPA-D attacks. So if you want INDCPA-D security, you have to be careful about for any type of schemes. What about countermeasures? For all schemes, you want to ensure a tiny failure probability, where the probability is only over the randomness of the inputs. And no heuristic noise analysis. And for CKKS, you also want high precision computation so that at the end of the computation, you can flood. So all this leads to efficiency questions. So how do you, I mean, for all these, we know in theory how to implement this. And then the question is, I mean, what is the cost impact of these countermeasures? And one has to be very diligent with the implementation as well, because for INDCPA security, you only have to be cautious about keygen and ENC. So that's where the security lies. For INDCPA-D security, you also have to be cautious about eval and DEC, because you need to be careful about the noise growth and the failure probability. Okay, so that's it. If you have questions, I'll try to answer.
Thank you. Very nice talk. I was wondering for your attack on TFHE RS, you cannot use, so the failure probability doesn't depend on the circuit. You cannot use a specific circuit to make it fail with a higher probability.
No, yeah, I mean, so for the basic CGGI, yeah, every gate is implemented with a gate bootstrap. So they're all the same. If you start playing with extensions where the plain text is small integers, I don't know. Maybe there are some gates that are, I mean, some functions. So then you talk about functional, I mean, they talk about functional bootstrapping. You evaluate a function while you bootstrap. we didn't consider this. So it could be that there are some functions that lead to higher failure probabilities. I didn't look into it.
Okay, thank you. And second question, you mentioned some use case for which the model is not, I mean, the attack is not relevant. But so can you like give examples of such use case and other use cases where the attack is actually relevant?
So if you don't give out the answer of the computation, if you keep the result for yourself, then INDCPA-D security is not relevant. So if you just delegate a computation and you trust whatever is given back to you, then INDCPA is enough. If you go to models that are beyond this, then it's becoming relevant. Even just reaction attacks, like saying that yeah, my result is flawed or weird. Please redo, and it's already.
Yeah, right. It seems a bit hard to avoid, like in practice, no?
Yeah, it raises important deployment questions. I mean, in some practical scenarios, you can also bound the number of queries that you make. So then, yeah.
Thank you.
Regarding the attack model, so if I remember correctly, you described distinguishing attacks, but distinguishing attacks, are they really relevant in like real life deployment, or would we only care about search attacks typically?
Yes, it's a good question. So I mean, key recovery attacks, I mean, these are like total breaks. Distinguishing attacks, I mean, in some cases, maybe it doesn't matter too much. Also, something I want to mention about reaction attacks, like if your result is weird and you are telling the server that your result is weird, it matters more for exact schemes than approximate schemes. Because if the result is 0 or 1, and you get a 0 and you were expecting a 1, then you will react. For approximate schemes, if you get a 0.98 and you are expecting a 0.93, yeah, maybe you will react, maybe not. So it's.
But for exact schemes, could you? I think you mentioned that in the talk, but could you just like you add noise before decryption, and then you're basically in the same good situation as with approximate schemes? To like hide the fact that it's 0 or 1, like it starts being a bit similar to differential privacy where you just.
Yeah, but to 0 or 1, how do I hide it? If I add a noise to 0 or 1, it has a tendency to become uniform.
Yeah, okay, then you would need, instead of encoding values in 0 or 1, you encode like a multiple of something and then you add some noise.
Yeah. So yeah, you need to start thinking about those stuff, yeah, in this case.
Just regarding the arguments for when INDCPA-D is not a relevant model, it seems you want to say that your behavior after receiving your ciphertext is independent of the value of the ciphertext when you decrypt it. Right? That would rule out INDCPA-D as being important if you don't condition your behavior on the decryption of the ciphertext that you receive back. Because it's not just about saying, oh, this ciphertext is wonky, send me another one. It's like your behavior being independent of your received answer, but then that seems quite strong as a statement to rule out the importance of INDCPA-D. Does it make sense?
Can you repeat, please?
Okay, sorry, I garbled that a bit. So your example is saying, okay, I've received a wonky ciphertext and do it again. And this is kind of like a partial INDCPA-D oracle. Well, to rule out INDCPA-D entirely as a relevant model, it's almost like you want to say that your behavior is independent of the ciphertext you receive back. But that's too strong, because if your behavior was going to be independent of the ciphertext, you'd have never bothered paying for the ciphertext. So I don't know, it seems quite a reasonable model to me. Okay.
Okay, so maybe one example that I have in mind at the moment, but I don't know if it is super relevant or if it helps understanding. So let's say you want to do ChatGPT homomorphically. So you ask a question, and what you get is a bit weird at the end. ChatGPT is already a bit weird sometimes, so maybe you're not going to react. I mean, that's
Now you need a model for how we advise.
yeah. Yeah.
Thanks.
Are there any other questions?
So as you said, all these error evaluation only take into account the error that is inside the the original ciphertexts, because all computations are deterministic. I would guess that's just for efficiency. So how would doing non-deterministic computation, like adding error during computation, affect things? And would it maybe help with those INDCPA issues, and would it completely destroy efficiency?
So, I mean, it will have an impact on efficiency because, I mean, the size of everything here depends a lot on the size of the errors. Like in a basic, like a PKE and signatures based on lattices, you want the tightest possible bonds on smallness because you can decrease Q. And if you are a bit non-tight on how you estimate things, and it blows up. So there will definitely be an efficiency impact. Maybe not catastrophic. But what I'm worried about is that it's going to be a bit tough to make sure that the error terms don't, I mean, that it still doesn't reveal anything. Like for example, the bootstrapping attacks, even if you add noise a bit before or whatever, I think they still work in this case. So yeah, that's one of the tools that we could be using, but it's not an obvious winner.
Thanks.
Practice or in theory? In theory, yeah. So sometimes they need INDCPA-D. Like all the stuff that involves multiple parties, threshold FHE, but multi-key FHE, I think there are multi-party FHE and so on. All this requires INDCPA-D. It requires more, but at least INDCPA-D. I think in many of these applications you need INDCPA-D as well.
Any other questions? If not, then let's thank Damien again, and let's take a coffee break.